Okay, good morning everyone. I'm Lucas, and today I want to talk about this paper. Okay, first, I want to explain why iron is the important element in marine science. Iron is necessary for phytoplankton growth. Moreover, in the HNLC regions, iron is a limit factor for phytoplankton. Therefore, it is important to determine the concentration of iron in phytoplankton to measure the iron to carbon ratio. However, there is a serious problem in the quantitative analysis of iron in phytoplankton. For the phytoplankton, it contains two types of iron. The first type is intracellular iron, which were used as nutrient by phytoplankton. The other part is extracellular iron, which will not be used as nutrient. Therefore, when we calculating the concentration of iron or the iron to carbon ratio, it will not be including, or otherwise the overestimated result will be get. So it's necessary to use the clean reagent to remove extracellular at first. At later, the most widely clean reagent is titanium EDTA citrate wash reagent, also called titanium reagent, but it has some serious drawbacks. The first drawback is its repair reaction with oxygen make it difficult to use, and a very short shelf life. It's only a few hours, so it must be prepared fresh every day. The second drawback is titanium reagent could cause cell damage to phytoplankton. The final and the most drawback is titanium reagent itself contains contaminated iron, which will cause analytical errors. Therefore, the purpose of this paper is to find a new effective, powerful clean reagent. And the one promising reagent is oxalate clean reagent, also called oxalate reagent. There are some important chemicals in oxalate reagent. Among them, the most important one is oxalic acid. The experimental method of this paper can divide into four main parts. The first part is preparing the oxalate reagent. They don't contain any contaminated iron. And the second part is iron removal efficiency and chemical stability experiment. The third part is cell lasers experiment. The last part is field study to test whether oxalate reagent is useful in analyzing a real environmental sample. Okay, we thought this is a iron removal efficiency experiment. We prepare 4 samples of the sand diatom culture and label them with iron 55, which was radio transfer, and more than 95% of 1955 was extracellular iron. And we wash 4 samples with different reagents, including oxalate reagent, titanium reagent, and 2 other reagents. Finally, we calculate the removal efficiency of iron 55. And this is chemical stability experiment. We test the iron removal efficiency every 13 days for 3 months, and observe the removal efficiency decrease over time. And this is cell lasers experiment. The same phytoplankton species cultures were exposed to oxalate reagent as experimental group and filled seawater as control group for 5 minutes. And we observed the cell density difference between 2 groups. Okay, and this field study. We prepared for the different real sample collected in the location marked on the map, and handle the samples with standard procedure. And then we divide the sample from the same region into 2 groups. One group was unwashed group. The other one was wash group treated with oxide reagent, and we measured iron concentration by GFAAS and compare iron concentration of the two at each region. The result follow this formula: extracellular iron equal to total iron minus intracellular iron. After completing all the experiments, I will now explain the results. This is the result of iron removal efficiency. As you can see, oxide reagent and titanium reagent has almost the same ability to remove extracellular iron. Both could remove 97%. In contrast, two other reagents show relative low removal efficiency, both of them lower than 18%. And it's a result of chemical stability. As future show, the extracellular iron removal efficiency remains about 19% for up to 16 days. But following 16 days, the removal efficiency decreased not stably. So we can say the oxide reagent is stable for up for 2 months in a suitable condition. Following this is cell lasers results. As we can see, among the different phytoplankton, there are not obvious difference between two groups. So we can say the oxide reagent is almost not damage the phytoplankton cell. Finally, this is a result of field study. This result show that oxide reagent is useful for analyzing the real environmental sample, and the percentage of extracellular iron strongly depends on the location. For example, the percentage of extracellular iron at first location was 86%, but at a surplus location, it was only 16%. So when we analyzing the real sample, we should consider is the extracellular iron a failure result. And now I want to explain the implications. The oxide reagent can be a useful and a powerful research tool in iron biogeochemistry because it allows us to analyze the iron at a very low concentration accurately. And it also helps us establish database of iron to carbon ratio. Both of them are very important parameters in the marine iron cycles. But it still have some limitations. For example, the oxide reagent may solve other forms of iron and some biogenic metals. Both of them will lead to overextending of extracellular iron. Moreover, another limitation is that for the real sample, the environment are much more complex, and the interaction between oxide reagent and the real sample environment is not fully understood. So it still need to combine with other clear reagent measure to improve the accuracy of result. In conclusion, the new oxide reagent accurately differentiate between intracellular iron and extracellular iron. Moreover, it is easy to prepare, chemical stable, and almost harmless for phytoplankton cell. In addition, this technique is very useful for any laboratory with AAS or ICP-NS to analyzing trace label iron concentration. Therefore, the ability of oxide reagent will allow a key variable in a marine iron cycle to be measured. And this is my references. Okay. My presentation is the end. Thank you, everyone.
I want to ask about how can we apply this oxalate reagent?
Or if you want to analyze the concentration of iron in phytoplankton, you have to use clear reagent, and it's very useful and convenient.
Thank you.
Can you explain what is a HNLC region?
HNLC region is mean high nutrient and low 叶绿素 low 叶绿素. And in this region, iron is limit feature for phytoplankton.
Thank you.
Okay. Well, what is the difference between surface bound iron and intercellular iron?
Surface bound iron is mean extracellular iron, which is only attached to the cell, and the extracellular iron is a nutrient which will be consumed by phytoplankton.
Okay, so Lucas, you were very familiar with the line. I can see that. But because this is not a biology talk, this is one of the few chemistry talk we have this class. So you see you have relatively many words. But you didn't use the pointer to guide us. So as long as my mind was a little bit distracted, then I lost track where you are. So it's especially important for you to use pointer to help us. That's very important. And of course, next time I hope you can look at them instead of look at this. And I found it very interesting because you said this is a paper I want to present next. So you didn't introduce that. What is the topic of your talk? So that's something you should do next time. And then in your introduction, it's good that Victor asked the question because you didn't explain it in your talk. I think you said a lot about the importance of iron, and you even highlighted HNLC, but you didn't explain it. And this is actually a very important part of the ocean for the iron cycle. So you should spend some time. You have time. And another thing which I think is missing is you talk about the intracellular and extracellular iron, but I don't know if you mentioned or the paper mentioned which one is more important for the physiology of the algae. Did they say that? I think they should have said that, so that's the reason they want to differentiate these two kinds of iron. So please say that next time. Which one is important for iron cycle? All right, and then please next time put it here. You see, I don't see the page number anymore. So, yeah, yeah. So, and how come that you don't know how to read chlorophyll? You should know how to read that. You are from Department of Oceanography. Okay. Okay. Then this part. Sorry, I don't know which page. 5 or what? Okay. Here there was where did you? Oh, here. I don't know how you read this. This read rapid. Rapid. There was a pronunciation issue, and here you talk about the drawbacks of the titanium reagent. This is good, but I really think you can find some icon to enrich your slide. You know, it's sad that chemists, they don't have too much image, but you can use icon. Icon is for everyone. And here it's good you look for the structure, and there's this is good to show us the structure of your experiments. This one is really nicely done, but I have a suggestion. Because after you finish this one, you started to talk about details of each experiment. The order of your the structure of your slide was you talk about all experiment and then you talk about their results. But you have to keep in mind that the memory of the audience is really short. So my suggestion is next time you reorganize your slides where you only need to tell us you have 4 kinds of experiments. Then you talk about experiment 1 and right after you talk about it, you show data. That would be easier for us to know, okay, that's what you did and that's the data. And here you have this nice animation, so I appreciate that. This is good. All right, because after this, I was thinking, okay, where is your data? Because you go to experiment 1, 2, 3. So then I realized you talk about all experiment together. So reorganize next time. Okay, result. Did you do this yourself? Oh, okay, that's really nice. So I appreciate that. So because that look different from the paper. So this is good, and you have this concluding sentence, and you also make the figure really large. That's nice. And this is from the paper, right? Yeah, but as I said, and when you introduce the figure, you, especially this one, you didn't introduce the axis. And as I said, they probably already forget, what's this? Why do you have time here? They, the audience. So that's the reason you should introduce experiment followed by this. And to say this is the maybe shelf life, shelf time or what, of the reagent. And that's the efficiency of the reagent. Okay. And this is also made by himself. This is good, but again, you didn't introduce the axis. You should do that. And this is also made by yourself, so I appreciate that. And okay. And you can you also show this clearly that it's site specific. All right. So right, the discussion part is okay. I don't know whether you can somehow enrich it with some icons because you see your slides were full of text. And this one is also okay. Okay, the conclusion is specific enough. So next time, as I mentioned in my previous comments, you have several places where you can improve. So I hope to see your improvement next time. Thank you.